Good afternoon, class. Okay. Today we're going to be talking about section 10-2, lines tangent to a circle. This is my third take now making the video since I can't pause. Unfortunately, Pearson has an evil blue packet because the numbers are not always what they seem. Okay, so if there is an error, bear with me. Okay, I'm trying to do it on my first attempt. But again, this is now my third attempt because numbers just don't add up. But we'll get through it. Okay, so we're going to talk today about tangents of a circle. If you want to go back to 10-1 to focus on arc lengths, arc sectors, feel free to access the online book, your notes, anything. But we'll be working out the blue packet. I did post it on Edsby as well, and you should also have a copy from before spring break. Okay, so there's these four conjectures right here about lines that intersect about a circle. What's Alicia and Ronaldo? It says, which of the four conjectures do you agree with? I would say all 3 out of the 4 are true. The only one not true is many lines intersect the circle once at the same point. Okay, and the reason why this one doesn't work is if I draw a point right here, the only line that intersects at one point is this line right here. Okay, there's no other way to draw a line going through this point that hits exactly one point without it going through the circle and hitting somewhere else. Because if it went through at this angle, it's going to hit here and here. I only want to hit it once. So any line, there's only one point. 2 lines that intersect the circle once in the segment connecting the point form an isosceles triangle. That's true. It'll be right there. And then these other 2 will be true as well. And we'll come back to them. Okay? So if a line hits a circle at exactly one point, we call that the line of tangency. Okay? Tangent just means a line that intersects the circle in exactly one point. In other words, it hits exactly once. Not twice, not 3 times. It hits exactly once on the circle. In other words, if I draw, and then let's say here, my line of tangency, it's going to hit at exactly this point, nowhere else on the circle. So I just draw a line that goes through that, like so. Okay, it will not hit anywhere else on the circle. It won't go through any other point, once on the circle. Okay, there are 3 theorems we're going to talk about for this section, and these are in your salmon-colored pen. Okay, this is on page 22. Okay, we're going to look at the bottom 3. Okay, and these are very straightforward. Okay, the shortest distance to anything is a straight line. So if I go from point O to R, it's a straight line. To go straight line, I make a 90-degree angle. So if a line is tangent to a circle, then it's perpendicular to the radius. So it forms a 90-degree angle. So if this is tangent to this point, it makes a 90-degree angle. The converse is also true. If I know it's a 90-degree angle, then I can say this line is tangent. So in other words, if it's tangent, it makes a 90-degree angle. Okay, and if it's perpendicular, then the line is tangent. Those are the 2 top theorems. Theorem 10-11. If I have some outside point, okay, and I draw 2 lines, one tangent to B, one tangent to C. The distance AB is the same as the distance AC. So in other words, AB is the same as AC if both are tangent. And you can show this using congruent triangles, and we're not going to worry about that. Just accept these 3 theorems as true. Now let's go back to our examples, and we'll look at page 446. Okay, so does example 1 support Ronaldo's conjecture that parallel lines intersect the circle at opposite ends? And yes, okay, they are parallel lines. Okay, so if I draw a radius, okay, O, and then draw the entire diameter. So if this is the center O, I draw a diameter going through it, and then I just say, here's my tangent point, and here's my tangent point, then these all make 90-degree angles by our theorem. And because these are alternate interior angles, and they're all 90, then we could say the alternate interior angles are the same, therefore the lines are tangent. They're parallel lines by alternate interior angles. Okay, so it will work. Okay, example 2a. Is MP tangent to circle N? Okay, in order for it to be tangent, this needs to be a 90-degree angle. So there's 2 ways you can do it. Okay, what I like to do is, because it has to be a triangle, angles in a triangle add to 180. So if this was 90, then these would add to 58, 90, and 33 equals 181, which is not equal to 180, so it's not a 90-degree angle. In reality, this angle would actually have to be 89 degrees. Okay, it has to be 90, so it doesn't work. Okay, now the problem is example 2. Okay, so ignore this right here. This is crap. Okay, they messed up in this example. This should be an x minus 1, not an x minus 4. I don't know why they wrote x minus 4. If it's x minus 4, then you get no answer. And because of their errors, third attempt, I hate wasting time. So that should be x minus 1. Okay, so what we're going to do is we're going to do this example right here. So I'm going to just do B up here. Okay, so because LK is tangent to circle N, that makes this a 90-degree angle. Therefore, this is a right triangle. Okay, so we can use Pythagorean theorem. A squared plus B squared equals C squared. That's true for any right triangle. So what I'm going to do is I'm going to draw my right triangle, labeling the correct letters. So I'm going to just draw it with the right angle at the bottom. Okay, and that goes with L. The other two I can put wherever. So I'll just put K here and here. So LKN. Okay, so we know LK is x plus 5. Okay, we know LN, this is going to be 9 because from N to any point on the circle, that's a radius. So from N to this point is 9. Therefore, N to L is also 9. There are radii of the circle. So NL is 9. And then NK is 9 plus x minus 1. And if I add 9 and x minus 1 together, that gives me x plus 8. Okay, so those are the sides of my triangle. Now I have to use Pythagorean theorem and solve for x. Once I know what x is, I can figure out the entire side. So my two legs, x plus 5 squared plus the other leg squared, which is 9, equals my longest side squared, which is x plus 8. Now I'm going to expand this out. And remember, when you expand it out, you're just multiplying it by itself. So really, this is x plus 5 times x plus 5, which is just x squared plus 5x plus 5x plus 25, which is x squared plus 10x plus 25. Okay, plus I have the 81 already. 9 squared is 81, and that's going to be equal to x plus 8 squared, which when I expand out, and I'll show the steps for some of you that have problem with the factoring or expanding out, x squared plus 8x plus 8x plus 64, which is x squared plus 16x plus 64. Okay, now I'm going to solve for x. First thing I'm going to do is just simplify this side first. X squared plus 10x, 25 and 81 is 106. The other side stays the same. Okay, notice they both have an x squared piece on each side, so I can cancel those out. Okay, now I'm going to solve. So I'm going to subtract 10x to the right side, and I'm going to minus 64 to the left side. So when I do that, okay, I'm going to minus 10x, and I'm going to minus 64. So now I'm left with 42 equals 6x. Dividing by 6, I get 7 equals x. That is my answer for x. Therefore, if this is x minus 1, this little piece is going to be 6. So the entire length of Kn will equal 6 plus 9, which is 15. And that is my length. Okay, so when they give you a line that is tangent, use Pythagorean theorem and solve for x. Once you know what x is, substitute back in and use that to find the length. Okay, you can also use Pythagorean theorem to show if it's not tangent too, because if it doesn't equal a squared plus b squared equals c squared, then it's not a 90-degree angle, and then you could say that is not a line of tangency. Okay, that was example 2. Okay, example 3. It says find lengths of segments tangent to a circle. Okay, so we're going to use the example in the book, and since they don't give it to you on the paper, I'm going to draw out the diagram. Okay, so just give me a second to draw out the diagram. me find it. Example 3. Here we go. Okay, so here's our diagram. Okay, so here's my circle. Okay, and then we have center T. This is a point of tangency. We'll call this X here. And then down here is Y. This is a point of tangency too. Okay, and then we have point Z up here. So, okay. So we know from earlier, one of the theorems, section 10-11, if I have an outside segment, boom, and it's tangent to 2 points, I know those are going to be the same length. Okay, so we're just going to fill it in. It says if tx equals 12, so this is 12, and tz equals 20, okay, what are xz and yz? Okay, so if this is 12, this is a radius, therefore this piece is also going to be 12. Okay, this piece is going to be, okay, bingo, we got it right here. Notice if this is, okay, this is going to be a right triangle, okay, since we know these are tangent, we know this is going to be the same distance. This is going to make a 90-degree angle, okay, because these are tangent at these points. Okay, even if it doesn't say it in there, it is from the previous example in the textbook that these are points of tangency. So we have a right triangle here. So if I draw the top triangle, okay, it looks like this. I have X, I have Z, and I have T. I know Tx is 12, Xz, I don't know. I'll just call that let's just call it M, and then we'll call ZT 20. Okay, now we're going to use Pythagorean theorem to solve. And yes, this is not drawn to scale, so people like you, Mr. Andre Skelton, okay, don't assume sometimes, okay? Just, okay, oh, this side looks smaller, whatever, just go by my diagram, okay? Even if it's not drawn to scale perfectly, okay? This is everything we need. Okay, so continuing. Okay, we know the two legs squared added together equal the biggest leg. So 12 squared plus the other leg squared, which we call m, equals 20 squared. So this is just 144 plus m squared equals 400. M squared equals 256. And then solving for m, I take the square root, m equals 16. Therefore, zx is 16. Therefore, okay, zx equals 16. And by our theorem, yz is also going to equal the same distance, because by our theorem, an outside point tangent to 2, those distances are the same. Okay, the last example we're going to look at is example 4. We're not going to worry about constructions, any of that. No need to. Just going to focus on the algebra. It says, what is the perimeter of ABCD? Okay, notice I see a lot of 90-degree angles. When you see 90-degree angles, you think right now, bingo, tangency. Okay, so I'm going to use my third theorem. Okay, so A is my exterior point, and it's tangent to this point and this point right here. So therefore, these two distances are the same. So if this is 7, this point from here to here is also 7. Now I look at B. B, it's tangent to here and here. Those distances are the same. So from B to this point is 2. B to this point is also 2. Same thing here with C. Tangent to here and here. So if this is 3, this is 3, and you get the idea. Here, D, distance from here to here, both the same. This is 6. Now I just add up these numbers around. 7, 9, 11, 14, 17, 23, 29, 36. So the perimeter will be 36. Again, let's see, 7, 13, 19, 22, 25, 27, 29, 36. So those are some basic examples with how to figure out the points of tangency. You will be working on your 10-2 assignment, which is 15 questions that deal very similar with it. You have unlimited attempts, and you just have to do some basic Pythagorean theorem, solving for x, substituting it in, or using your basic definitions. Let me know how this video went. You can give me some feedback. I'd like you to be honest. Again, it stinks when you can't pause the video, and if you make an error, you just got to go with it. So this is Mr. Holmes, and saying have a good rest of the week. 10-3 we will focus on later in the week. Take care. God bless.